The following video is on Newton's method. Finding roots of functions, including polynomials, is hard. We have a formula for finding the root of a linear equation, ax plus b. We also know the quadratic formula for finding the root of a quadratic equation. There are similar rules for cubics and quartics, so degree 3 and degree 4 polynomials, but we don't cover them in this class. But the interesting thing is that there's no formulas for general polynomials of degree greater than or equal to 5. So you'll never be able to generalize how to find the roots. Notice also that these formulas only work for polynomials. Other functions in general have no such formula. So in science, we often would need to find the roots of functions. The problem for today is, how do we do it? So we're going to do something called Newton's method. Below you see the graph of a function, and we want to try to approximate where this function crosses the x-axis. Remember, that's called a root. I'm going to make an initial guess, which I'm going to call x sub 0 or x naught. And my initial guess in this case is going to be at x equals 1. Notice that x equals 1 is sort of close to the actual root, but not exactly the root. So now I'm going to drop my line down until I hit the curve. I hit the curve at the value f of x naught, and I'm going to draw the tangent line at that point. Where the tangent line crosses the x-axis, that's going to be my new guess. In this case, x1 is my new guess, and it's going to be at the value 1.5. Notice that x1 is slightly closer to the actual root than my initial guess was. I can now repeat the process if I want. I can take x1 up until I hit the curve, so f of x1, and then draw a tangent line at that value. Where this tangent line crosses the x-axis is my new guess, which this time I'm going to call x2. Notice that again x2 has gotten us slightly closer to the actual root. And we can keep going with this process until we get as close as we want to the actual root. This process is called Newton's method, and it is named after Sir Isaac Newton, who we discussed in a previous video. Let's do an example, or actually let's first talk about how to use Newton's method. So starting with an initial guess of x sub 0, we want to find the y value f of x sub 0. We will then draw the tangent line to x sub 0 comma f of x sub 0. So we'll draw the tangent line at that point. And then we need to find where the x-intercept of that line is. This new value is going to be our new guess. And we can continue this process as instructed. So how do we actually find the x-intercept of the tangent line? First, we'll find the equation of the tangent line at x naught comma f of x naught. The slope is going to be f prime of x naught. That's the slope of the tangent line given by the derivative. And so using the point slope form, we have y minus the y value equals the slope times x minus the x value. In order to find the x-intercept, we set y equal to 0 and solve for x. So we can divide both sides by f prime of x naught, and then add x naught to both sides. So we have that x equals x naught minus f of x naught divided by f prime of x naught. And this is our new guess. Remembering this process is not difficult if you can just remember how to make the following chart. In the first column we have n. That's how many iterations we've done. The second column is x sub n, and that's the guess. The third column we plug in f of x sub n, so we want to find the y value. The fourth column we take the derivative and plug in our x sub n. The fifth column will take the third column, f of x sub n, divided by the fourth column, f prime of x sub n. And in our final column, we will use x sub n minus f of x sub n divided by f prime of x sub n, which remember is the new guess. So let's try an example. Let's approximate the roots of y equals x cubed minus 2x minus 5 with initial guess of x naught equals 2, and we'll do 2 iterations of Newton's method. So we start with n equals 0. Our initial guess is going to be when n is 0. And x sub n, our initial guess x sub 0, is 2. When we plug 2 into the function f of x, we end up with negative 1. Now we need to find the derivative of our function, which we know by now is 3x squared minus 2. And I can plug x sub n into my derivative and end up with 10. Next we do negative 1 divided by 10, which is negative 0.1. And finally we're going to do x sub n, which is 2, minus negative 0.1, so I end up with 2.1. Now we're ready for our next iteration of Newton's method. So n now goes up to 1, and x sub n, remember, is the whatever value we had in the last column of the previous row. So we repeat the 2.1 for x sub n. Now we plug 2.1 into f, and using my calculator I found that that was 0.061. I plugged 2.1 into the derivative, and again using a calculator I found that that was 11.23. Now I divide 0.061 divided by 11.23 to get 0.0054, and then we do 2.1 minus 0.0054 to get 2.0946. N then iterates up to 2, and we repeat the value of x sub n, 2.0946. And since we needed to do 2 iterations, and we're now at n equals 2, we can stop. Our final answer is 2.0946. In fact, if we try plugging in x equals 2.0946, we get y is approximately 0.000541. So we ended up with a pretty good approximation of the root to this equation. The y value at 2.0946 is 0.000541. But if we needed to get an even more accurate approximation, we could just repeat the process again and we would get even closer to the real root. Repeating the chart again, let's try another example. Let's use Newton's method to approximate the value of x such that cosine of x equals x. And this time we'll keep going until 2 consecutive guesses differ by less than 0.0001. Notice that if cosine x equals x, then cosine x minus x equals 0. So let's let the function f of x be cosine x minus x. Notice that that means that the derivative, f prime, is going to equal negative sine x minus 1. And now we're ready to start filling out the table. Notice that we weren't given an initial guess in this problem, so we need to find an initial guess. We're going to try x naught equals to 1. I just picked 1 at random and tried plugging it into the function, and I saw that cosine of 1 minus 1 is negative 0.45969, which is fairly close to 0. The better that your initial guess is, the fewer iterations you'll need to do. So if n is 0, x sub n is 1. Remember that x sub 0 is 1 in this case. If I plug in f of x sub n, that was the problem I already computed, the negative 0.45969. If I plug in 1 into f prime, I get negative 1.84147. If I do f of 1 divided by f prime of 1, I get 0.24963. And if I do 1 minus 0.24963, I get 0.750368. This is now my new guess. So if n is 1, x sub n is 0.750368. I'm now going to plug this into f of x sub n. So I have negative 0.01893. I can plug x sub n into f prime of x sub n, and I end up with negative 1.6819. I can now do f divided by f prime, and I get 0.011255. And then I can do x sub n minus this value to end up with 0.739112. Notice that the value in the second to last column is the difference between the previous value and the current value. So my guess currently differs by 0.011255, which is not enough for us to stop. Remember, we wanted to keep going until our consecutive guesses differ by less than 0.0001. So let's move on. N is now 2, and x sub n is 0.739112. F of x sub n is going to be negative 0.000046. F prime of x sub n is negative 1.67363. The ratio is 0.000027, and the final value is 0.739139. This time, the difference between these two values is 0.000027, which is what we were looking for. They differ by less than 0.0001. So our final answer is 0.739139. Sometimes Newton's method fails to work. Let's look at an example of this. Here our initial guess is x0, which we trace up till we hit the function. Then we look at the tangent line to get our new guess. So x1 is my new guess. I trace it up until I hit the curve, f of x1. Then I look at the tangent line, and that gives me x sub 2. But notice that x sub 2 in this case is the same as x sub 0. So what we end up doing, instead of getting closer and closer to the root, we end up going around in circles forever. We can see another instance of this. Again, this is an S-shaped curve. If I choose my initial guess, x sub 0, and trace it up till I hit the curve, then trace it down until I hit the x-axis, I get my new guess, x1. I repeat the process to get my new guess, x2, repeat the process to get x3, and repeat the process to get x4. And notice that what's happening is we're getting further and further away from the initial root. Finally, remember to be careful not to let your guess be at a horizontal tangent line. If this happens, f prime of that guess is going to equal 0 because the slope of the tangent line is 0. And what that means is that f of x sub I divided by f prime of x sub I will be some number divided by 0, which we know does not exist.